All right, everyone. So we're doing chapter 18, electric potential energy, and a capacitance. So in this chapter, we're going to talk about potential energy. It's the same type of potential energy we covered in physics 6, in mechanics. Remember, there's a gravitational potential energy, there's a spring potential energy, and this potential energy, remember, is type of energy that can be stored and then can be used to convert to other things like kinetic energy, for example. So this type of potential energy is also can be, found in electric interaction. That means electric potential energy is type of energy that can be stored due to electric fields, electric forces, and it can then be used to convert into kinetic energy. But there's one extra thing that is we're covering here that we didn't really learn in physics 6, and that's potential, which is different from potential energy. So there is a potential energy and there is potential. So electric potential or potential. So we're going to talk about that. We're going to make sure that there's a good understanding of the difference between those two. They are related, but they're two different things. And we're going to then talk about equal potential surfaces, which means that equal potential means equal potential surfaces. And we're going to finish then the chapter with learning about capacitors. And this is going to be our first introduction to building a circuit. So capacitor is a circuit device that's going to be used to, for example, store energy. All right. So, and obviously, we're going to try to find a way to calculate that, let's say, field energy, right? Electric energy, electric potential energy. Okay, so before we start, there's a quick review on what the energy, so like let's say is, remember, so and how we transfer energy into the system. We learned in physics 6 that in order for the object to go from this initial position to the final position, that means for the object to undergo a displacement, one of the things we can do here is that means this object needs to have a motion. That means there has to be a motion for this particle to go from point initial to point final. And how do we provide that energy for motion? If you remember, we call that kinetic energy, right? Well, that energy of motion comes from a force that we exert on the object. And when there's a force acting on the object, and then that force makes object to change the position, then we can say that the amount of energy in the system increased or decreased due to that force acting on the system, on the object. That means we had this work done, right? So this W, which was proportional to the magnitude of the force, and it was proportional to the displacement of the object. And we also had then the cosine of angle between them. So if you remember, we talked about that this is, so let's say, amount of work done by some constant force. In this case, force is constant, or let's say. So if you know then the work done is due to a constant force, then you can use this equation to calculate the work done. So this is the summation sign, which means that you can have the work done due to different forces. For example, let's say you have a box going from this initial position to, let's say, this final position. So you can have, let's say, for example, force 1. You can have maybe, let's say, force 2. Those two forces will do work because then there's going to be displacement. Maybe they're going to have a force 3. In this case, for example, force 3, we're going to be doing a negative work because the angle theta, see, for example, theta 1 here is 0 degrees because we are doing with respect to delta S vector. That means as you go from this initial position to that final position. So let's say if you have, let me do this. So say this is your displacement vector, right? Delta S. So remember this theta here is then with respect to that. So theta 1 here is 0 degrees. Let's say theta 2 here is 30 degrees maybe. And when you plot this magnitude of the force, magnitude displacement, cosine of angle, you're going to get a positive work done, which means energy transferred into the system. But for example, then this F3 has an angle of 180 degrees. That means the work done by this force 3 will be negative, right? So it's F3, its magnitude times displacement, then times cosine of 180. So it's going to be negative F3 times delta S, since cosine of 180 equals to -1. And then what we do here is we calculate the net, which will be work done 1 plus work done 2, let's say, plus work done 3. And then you calculate the total amount of work done. And then the total amount of work done was equals to always delta K, which is, when you transfer energy into the system can use that energy to move, for example. It can use that to change height, for example, and number of things. So one thing remember here is that this particular equation that I have is for the constant, let's say constant force. And sometimes force can be variable. And then in that case, there are other ways of calculating, let's say, the work done. And one of the things we can see here is this equation has to be used with electric potential energy, right, and electric forces, only when you know that electric field, for example, is uniform. In this case, you can use that. But electric field is not always uniform, because if you have two particles distant r from one another, and then when they change their position with respect to one another to, let's say, 2r, then you are changing the force between them, right? Which means that as the particle 2 goes from point 1 to point 2, the force between them changes. So it's a variable force, not a constant force. So this equation doesn't always apply. All right, so we will see then other ways that we can calculate that. Now, in any case, so let's again review one of the other type of potential energy that we covered last time, and that was the gravitational potential energy, because there is a really good analogy, right? There is a really good similarities between gravitational potential energy and electric potential energy, where you know that, let's say, for example, the electric field is uniform and constant. So for example, here what we have is an object. Let's say here's our object of interest. And this is, let's say, our initial position, right? So let's say this is initial position. And then it goes to the ground, which is our final position. If you want, we can say that, okay, this is point A, then this is point B. Okay, kind of like going from point A to point B. Now, if you remember, I talked about electric fields similar to what we call gravitational fields. That means this entire region is filled with the gravitational fields, which always point toward the center of Earth. So that means they're all straight down. And these gravitational fields for this particular, let's say, when you go from this y initial to that y final, for example, it's not necessarily that big of a change in height, or not that much height from the surface of Earth. So technically then you can say that G here is constant. That means this gravitational field. Then in that case, then what we have is this. Remember, the gravitational force was equals to m times G. Okay. Then remember, then the work done is equals to force times displacement. Then what we would do here is, then we would say that work done is equals to magnitude of the force mg, then times displacement delta y, which is then work done is equals to mg y final, or yb, let's say, minus ya. And if you remember, we defined gravitational potential energy as ug, which is then mgy. And then that means this is nothing but ub minus ua. So technically this is the, this is the equation for that. All right, so now that means final minus initial. But one of the things we have here is this. So you can see, right, when in the case of gravity, the work is done given with this equation, as I showed you, right? But there is a little bit of, differences because this is initial minus final. Well, that's because when the work is done by the gravitational force, this is equals to negative delta U, negative of change in potential energy. Because one of the things we can see here is this. When object goes from A to B along the direction of the G, right? So let's say this is your displacement in the same direction as the gravitational field, right? That means in the same direction as the field. the potential energy decreases. If you remember, right, point A has higher potential than point B if we take point B to be 0, for example, as our reference point. Then one of the things we can have here is we can see that when gravity is doing positive work, so you can see here, right, the gravitational field does work on the particle, okay? And that work done is in this case positive because the motion, right, this delta y, is in the direction of the force, and the force is also down. And if you remember, right, work done is positive, for example, if force and delta S same direction. And work done is negative if force and delta S have opposite directions. So in this case, when object goes from point A to point B, let's say the work done by gravity is positive. So work done by gravity is positive, but potential energy decreases instead of increase. So that's why this negative indicates that. That means when gravity doing positive work, potential energy decreases. And then this negative means that if I do the negative YB minus YA, well, then this makes it then YA minus YB. This negative, if you incorporate that, becomes initial minus final. And this is because gravitational force is a conservative force. And this is true only for the conservative forces. Because when a conservative force, you can see, right, conservative force doing a positive work, potential energy decreases. Same way this, work done by the spring force is equals to negative U spring, sorry, delta U spring, because when the spring force is doing work, it changes spring potential energy or elastic potential energy. This is also equals to, let's say, U spring initial minus U spring final. Okay, so that means, remember then, if the, let's say, if the motion of the particle is in the direction of the field, if it's in the direction of the field, work done by that field is positive, but potential energy in that case decreases. All right, so remember, so we have that. That means changing gravitational potential energy is then work done equals negative U of the gravitation. That means positive work done decreases potential energy. Negative work done increases potential energy. Now, what is a negative work done? Well, negative work done will be this. If you start from the ground and go some distance up above the ground. See, in this case, this is displacement, right? Delta U. But as the particle goes up, the entire time the gravity here is acting down, right? See, that means you can see, right? Force and displacement in opposite direction, which means work done by the gravitational force in this case is negative. Well, if work done is negative, that means delta U is positive and increasing. So that's the idea. Because we know, right? If YA equals 0, and let's say YB is equals to 1 meters, as you go from point A to point B, you go to a higher, vertical position, which means your gravitational potential energy increases. But the entire time, gravity acting in the opposite direction, which means it's doing negative work. Okay, so that's going to be very useful for us because we're going to be then using this for electric potential energies, because electric potential energy has very similar format. You can write work done is equals to U initial minus U final. All right. So let's now look at then same type of scenario, but for the electric, let's say, interaction. Now, in this case, we're assuming that, okay, so this is a particle that technically has a mass and there could be gravitational force acting on it, but electric force is so much stronger than the gravitational force is basically negligible. In this case, we are only looking at electric interaction and electric potential energies and things like that. All right, so this is a configuration that I actually talked about in chapter 17, and I think in the lecture that we talked about. So if I take two plates, so think like this, here's plate at the top, and I make it positively charged, and I take another plate and make this negatively charged, and D here is the distance between those two plates, and let's say those plates kind of like extend, you know, they're very long, so let's say. And if I have this configuration, then what I'm going to get here is I'm going to get an electric field. You can see, right, electric field going from positive to negative. But one of the things also we get here is this is a uniform electric field. Okay, it's a uniform, which means you can treat this as constant. Okay, you can treat this as constant. Now that means there's a downward electric field. So, which is kind of similar. See, if I kind of like set it up as a ground. So this is Earth, and this is, let's say, ground, right? So think like this. Here's point A, which is starts from the positive plate, which is, let's say, if I take here's point A. And what I have here is then, think like this. Remember what we had in terms of this equation. Force is equals to Q times E. And this is a test charge. That means this electric field is generated due to this source charges. So see, this plate is a source charge, is a positive source charge. Let's say Q1. And then the bottom plate is another source charge, in this case, negative source charge, Q2. What we have then, there is an electric field from Q1 to Q2, right? So that means there's, remember, so if you have two charges, so positive and negative, there's an electric field going from here to there. And if you extend them as a sort of like, let's say, plates, then electric fields, instead of curving, it's all kind of like, let's say, straight from plus to minus. Okay. So let's say technically if it ends right here, then you could see some electric fields kind of like curving like that. But if it doesn't, let's say if it extends, then somewhere in the middle of that configuration, you can find a lot of, you know, uniform electric field lines. All right, so then here's what we get. That means there is electric field, you know, in this direction, right? So this is like, let's say, electric field, just like then there's going to be, let's say, gravitational field. Okay, that means those are, you know, electric fields. Now what I do here is I place a particle right there. See this particle, let's say I put it here at point A. Now, because then there is electric field over there already in that region, there is going to be an electric force on that particle. Okay. Now, what I have here is, you can see, right, using this equation, I can see then because there's an electric field and I put a charged particle, there's an electric force. In which direction is the electric force? Well, it depends. Let's take this particle to be then, for example, positive. Then remember, if this is positive, then force is in the same direction as electric field, which means the force will also be downward. So if the force is downward, then it's going to make the particle go from point A to point B. And this is point B here at the negative plate. And this is similar to if you put the particle at if you put object of mass M at point A, right? There's going to be then gravitational force. And there's going to be gravitational force acting on it. Okay, sorry about that. So then this force is going to be in this direction, and it's going to go move the particle from point A to point B. So let's say that's A, this is B. And we can say work done by the gravitational force is positive because displacement is in the same direction as the field, right? This is delta Y in the same direction as the field. Then gravitational potential energy then will be negative because it means it's going to decrease. Well, same thing we have here. If I have then particle at point A, and there is a force on this particle pushing it from A to B, because of the configuration, right? Because as soon as I put the positive charge at point A, it's going to be then pushed, right, by this force. It's going to be pushed toward B, okay, or pulled toward B if you want to. And this particle then going to move from point A to point B. And if I'm looking at potential energy at point A, comparing it to potential energy at point B, what I can see here is this. Potential energy at point A is greater than potential energy at point B. That means as the particle goes from A to B, potential energy decreases. And what we have here is, that means the work is done by this force decreases potential energy. That means we can get two information out of that. One, electric force is a conservative force. Means electric force is a conservative force. Which means it will conserve mechanical energy, or it will conserve total energy. And that means then if you go from point A to point B, right? If you go from point A to point B, your electric potential energy, right? Then will decrease. Your electric potential energy will decrease. All right, so let's kind of clean this. Okay. You can see, right? So now what we have is this. If the field exerts a downward force on a positive charge, that means we're looking at, right? So there's a downward field, and if you put a positive charge, and those are the key. You have a positive test charge. So positive test charge has a force in the same direction as the electric field. That means there's a downward force. All right, so what does it do? Well, it's gonna make the object go from point A to point B. So then as the charge moves downward from point A to point B, the work done by the field is independent of the path the particle takes. Now, what does it mean? It means that if you look at potential energy at A and you look at potential energy at B, and then you do delta U, right? Which is then, you know, in terms of YB minus YA, which is the change in potential energy, you're going to get the same change in potential energy if you go in a straight path, if you go like this, or if you go like that, or if you go like this. Doesn't matter. Doesn't matter how you go from point A to point B, your potential energy will be exactly the same amount of change. That means delta U is same regardless of the path taken, which, remember, is the important thing about the conservative forces. When the conservative force does work, it is independent of the path. Now, what it means is then electric force is a conservative force. Now, electric force being a conservative force means that what we can think of here is this. If the positive charge moves in the direction of the field, right? So remember, so let's say this is my point A, this is my point B. So if I have then point A here at the top, point B here is at the bottom, right? That means it's a positive plate at point A, B is at a negative plate. That means I have a positive test charge and it moves in the direction of the field. Then the field does positive work. Again, why does field do positive work? Because see the direction of the force and then direction of the displacement, this blue over here, right? They in the same direction. Means work done by this force is positive. Okay. Now, remember the second condition, if the work done is positive, then the potential energy decreases. Okay. So now, this is basically same as gravitational potential energy. That means you go from some point above to the ground, gravity does positive work, your potential energy decreases. So this is analogous to that. Okay. The only problem with electric interaction is that you also have a negative charge, which kind of does exactly the opposite. But let's look at first in terms of the positive charge, both scenarios, and then we'll tackle the negative one. So that means here, because particle goes from point A to point B, a force does positive work. Because see those two arrows in the same direction. That means force is in the same direction as the displacement of that particle. Potential energy decreases. That means potential energy at point A is greater than potential energy at point B. You are decreasing your potential energy. Okay. Now, if we do other way around, that means, for example, I take this particle and put it point A here. Remember, if I put the particle at point A, remember, there's still a downward electric field, right? There's a downward electric field from positive toward negative. And this particle direction, this force direction, right, is independent in which direction is going to be moving. Because this force only depends on, if it's a positive charge, right, only depends on the direction of the electric field. So that means force, same direction, right? Remember? Same direction as electric field if Q naught here is positive. That means it doesn't matter where I put this charge. Like let's say if I put it here, or I put it there, or I put it here, there's going to be force in this direction. right? There's going to be force in all of those directions. Now let's then look at what we have. That means if I put this here at point A, the force is already downward. But now what I want here, I want this to go to point B. Okay, then what do we do here? Let's say we move it from point A to point B. Now you can see, right, then theta between those displacement and force is 180 degrees, which means that if positive charge moves in the opposite direction of the field does negative work, because going from A to B, force is always in opposite direction, so it does negative work. But the consequence of that is this: potential energy increases, because potential energy over here at point B is greater than at point A. Okay, it's kind of similar to, because so if this is being the ground, so if you go above the ground, right, so a point above the ground, you're increasing potential energy. So basically the same thing is here. All right, so again, if the particle has a negative work done by electric force, potential energy increases. All right, so let's continue now to the negative charge. So this is where things kind of get confusing sometimes, because for the gravitational potential energy, there is no negative mass. But for the electric interaction, right, electric potential energy, you can then be dealing with a negative charge. So let's see what happens. So I put the negative charge here at point A. So the point A has electric field, same direction as before. That means there's a downward electric field, right? That means electric field going from positive plate to the negative plate. But using this equation, we can see that if my test charge is a negative test charge, it means like electron or just a negative charge, then force will be, let's say, proportional to the negative of direction of the electric field. That means force is always in the opposite direction of electric field, which means in this case, you can see, right, force is upward, where electric field is downward. Remember, that's always the case. Force on the electric, sort of like, let's say, force on the negative charge, always in the opposite direction relative to the electric field. Remember, this electric field is there already, downward. I put a negative test charge, the force that it will experience is going to be upward. All right, so, but I want it to go from point A to point B. And you can see, right, then the direction of the displacement is down, where, you know, at the same time force is acting upward, which means then if the negative charge moves in the direction of the field, that means you can see, right, field direction is downward and the particle is moving downward, then the field does negative work. Why? Because the force is upward and this angle between them is 180 degrees. So work done here is negative. Well, when the work done is negative, remember, then delta U here is positive, means potential energy would increase. So potential energy increases. Again, the work done by this electric force is negative because electric force acting in the opposite direction of the displacement of the particle. That means we are technically, we're forcing it to go from A to B. We're forcing it to go from A to B, and gravity, electric force does negative work, but potential energy increases. You can see, right, this is kind of like exactly opposite of what positive charge would have had. So because positive charge going in the direction of the field, would increase potential, so would decrease potential energy. But here we have then increased potential energy. Okay, so in this case, potential energy increases. But the kind of like, let's say what we have here is, one thing is kind of similar here is this. So if a charge moves in the direction of electric field, right? So in this case, field does negative work. So if field does negative work, remember, field does negative work, potential energy increases, right? So let's look at here. So remember, so if field does negative work, potential energy increases. So if I go to the positive, here I also have, if the field does negative work, potential energy increases. That means you have kind of different directions and things like that because of the type of charge you have, but the condition is still the same. So you need to figure out, is the field doing negative work or positive work on that particular test charge? Because if the field does negative work, and the test charge is positive, potential energy increases. Well, the same thing is true for the negative. If the field does negative work, potential energy increases. It's just the direction of the displacement and direction of the force just happen to be the opposite because of the, you have a negative charge this time around. Because remember, so this negative test charge, if you put it there, is going to be automatically pulled, right? Going to be attracted to the positive plate. So it's going to be attracted to the positive plate. So there's a force, pulling it toward positive plate. But what we're going to do here, we're going to actually, force it to move in the opposite direction. As we force it to move in the opposite direction, we are increasing its potential energy. Just like you take an object, right? Take a piece of rock. See, if you holding the rock, the gravity wants to pull toward Earth. So if you let go, right, that force is pulling it down. But if you take it and move it up, you're moving it against the field of the gravitational field, right? Against the field. So the gravity doing negative work, but potential energy increases. It's the same thing, right? Anytime the field does negative work, potential energy increases. Which means that if then you have the negative charge moving, let's say, moves opposite the direction of the field, and then the field does positive work. Now the key here is that field does positive work on this charge, then potential energy decreases. Which means that, for example, if I take the electron here at point A, see, there's already a force acting on it. See, the field here is down. Field is down, but the force is upward. Force is upward because of the configuration. And now the displacement that I want is also in the direction of the force. Okay, that means that there's a positive work done because displacement and force in the same direction. Well, if there's a positive work done, it always will decrease potential energy. Okay, so the potential energy decreases. Okay, in this case, for the electron, if the field does positive work, potential energy decreases. Again, if you go back, you look at for the positive charge, exactly same thing. If the field does positive work, your potential energy will decrease. All right. So some things to review, right? So the work done by electric field of one point charge on another does not depend on the path taken. So for example, here's my source charge and it generates those electric fields. And I'm going to take a test charge, right? This guy, and start moving from point A to point B. That means what I'm doing here is I'm changing the potential energy. I'm changing the potential energy, which is basically YB minus YA. I'm going to change potential energy. Now, by how much potential energy changes, it only depends on two things. What is the potential energy at point A? What is the potential energy at point B? And then you take their difference. How you get there doesn't matter. Why? Because electric force is a conservative force. That's the key. And conservative forces are path independent. So that's kind of like the important thing. You can go like this, you can go like that, you can go like this to that point B, doesn't matter. Your change in potential energy is exactly the same. And one equation that then we can always use, right, is that, work done by the electric force is equals to negative of change in electric potential energy. So remember, I showed you that equation, right, for work done, which is force times displacement times cosine theta. Generally, we don't want to use this equation because, let's say, for example, something like this. See, for this case, what I have here is look at point A. So at point A, the electric field has a different strength than at point B, right? Those are different strength electric fields because different distance from point Q, from this charge Q, right? Remember that electric field strength is K Q over R square. Remember the magnitude of the electric field? You can see, right, RA is smaller than RB. That means electric field at point A is different from electric field at point B. That means it's not constant. So do not use this equation here. You're not going to get the right answer. But we can use this equation here. Okay, we can use that equation if we know how to calculate electric potential energy at point A, calculate electric potential energy at point B, and then, do their difference. But because of this, right, because of the work done is equals to negative, so work done by the electric force, because it's equal to the negative of the change in electric potential energy. So this becomes potential, something like this. It's negative final minus initial, but this negative then becomes distributed inside, so it becomes potential energy at A, then minus potential energy at B. That means you are doing initial potential energy minus potential energy, final potential energy to calculate work done by the electric force. All right, so we'll do an example. Now, how to calculate potential energy? So let's say you have a particle here. So let's say this is Q. And remember, so then this Q technically generates electric field. So let's say here's the electric field generated by this guy. Then, for example, and this is electric field lines, right? Kind of simplified electric field lines. So let's say then I bring and put a second one. So let's say here's my test particle, Q prime. Then what I get here is this potential, electric potential energy between, for this configuration is equals to K, Q, the source charge Q, Q prime, the test charge magnitude, right? And divided by their separation, not squared, but divided by their separation R. So this equation then gives you the electric potential energy for these two charges, okay? That means what you have here is, for example, let's take K to be 2 nanocoulomb, and it's positive. Let's take Q prime to be negative 3 nanocoulomb. Now, what do we do here? Well, in this equation, let's say then the R is 2 meters. So we have same K, 9 times 10 to the 9. Then Q, well, Q is 2 times 10 to the negative 9 because it's a positive charge, right? Then Q prime, well, Q prime is a negative charge. Well, remember, this is a scalar quantity. This is not a force. So you do put that negative over there, negative 3 times 10 to the negative 9 coulomb. That means you do put the negative in this equation. Then this is divided by the distance. So let's say 2 meters, not squaring it, just divided by 2 meters. And then let's say whatever you get from here, some certain number of, let's say, joules, right? And obviously, because there's a negative there, so you're going to get a negative, okay? So the negative number, I don't have a calculator, unfortunately, so I can't calculate, but, let's say we get that. All right, so then here's what we can have here. Well, actually, maybe we can calculate this. So see, this 10 to the 9 cancels that 10 to the negative 9. This 2 can be canceled with that. And then it's 9 times negative 3, which gives you negative 27 times 10 to the negative 9 joules. Okay. So I guess we can do that. It's an easy calculation. So, and that's what we have. And it's a negative electric potential energy, okay? So that means that potential energy, right? You can see, right? So electric potential energy of 2-point charges only depend on the distance between the charges, okay? So let's say if I take this, for example, right? If I take this to be point A, then this will be RA, okay? And then this will be what is the potential energy at point A. That means, when those two particles, two charged particles, right, separated by this distance RA, then I can calculate what is the potential energy, at that particular position. Now, if I move this particle, for example, from here to, let's say, there, that means this is then point B. Then what I have here, then this is RB. Then what I would calculate here is the potential energy at point B, which will be K, Q prime divided by RB, okay? Now, what we're gonna get here is the difference between those two, right, is just a distance, okay? It's just a distance. So let's say in this case, let's say the distance is 3 meters, right? So what will happen? Will the potential energy then increase or decrease? Well, remember, if this number here is bigger, that means you're gonna get a smaller number. So let's say again, if I do the same thing, right, in terms of then 3, so you should be getting then a smaller number. okay? And in that case, remember, so what you can have here is, look at position, and this is going to be some negative number again. So you can just run out of room to calculate. You can just try to calculate it at home. So then what we can do here is, this is going to be electric potential energy at point B. And then the work done is UA minus UB. Just calculate this. I have an example where you guys can see that. We're going to do an example. But in any case, so this is kind of what we can do and look at in terms of what we have for the, let's say, potential energy. Again, this is the potential energy between two charged particles at some very specific distance. Right. So this equation is valid no matter what the signs of charges are. Okay. As I said, we don't put absolute value because electric potential energy is a scalar. So then the potential energy is defined to be 0 when the charges are infinitely far apart, which, as you can see, right? So let's say here are Q, and let's say this is, I don't know, Q prime, and they're, you know, separated by its distance R. Remember, when you look at delta U, which is change in potential energy, this is potential energy between 2 points. And it's always easier when one point that you're considering is a reference point where potential energy is 0. Looking at this equation where U is equals to KQ prime over R, one position where this entire thing becomes 0 is when R is equals to infinity. Because if I replace this with infinity, that means they are infinitely far apart. That means, so let's say this is point B and then point A when, you know, when this particle was here at infinity. Because then what I can say that when, you know, YA is infinity, for example, right? Then there was no potential energy. Just like when object is on the ground, potential energy is 0. And then when you move that from point A to point B, some distance above the ground, then you have potential energy, right? Same thing here. So UA equals 0. Then what you want to do here is how much work do you have to do, right, to bring this charge from point A to point B? Why do you have to do some work? Why there has to be, you know, potential energy stored? Because remember, this is a Q prime. So the Q prime is positive, Q is positive. So if you have a Q prime, which is positive at point A, it's not going to want to move on its own toward the, positive source charge to the point B. Why? Because positive, it's always going to be repelled. That means in order for this guy to move from point A to point B, you have to push it. And when you push it, you transfer energy into the system, and that basically becomes the stored energy in the system. Just like you take a piece of rock, it's not going to want on its own to go some height h above the ground, right? You hold the rock on its own, it's never going to go. You have to actually push it upward, and then what you do, you store energy. Pretty much same idea. Okay. This diagram basically tells you that if you have this configuration, positive, that means two charged particles that you're considering, positive, or negative, because here's what you have. U is equals to KQ prime over R. Well, if it's positive, then your U here is positive, because, the entire thing becomes a positive energy. When U here is, let's say K negative and negative, let's say, right? They also negative cancels each other, and it's also positive. That means, your U here is positive for these two configurations. Means, potential energy, let's say you can say, right, as R reaches 0, potential energy, gets closer to the infinity. Okay, because remember, U is equals to KQ prime over, think like this. When you're infinitely far apart, those two charges, right? So let's say potential energy is 0. So you can say, right, as you go towards infinity, potential energy reaches 0. So this is 0. Y-axis is the potential. But as you get closer to R, right? See, as U gets closer to 0, like R has become 0, so 1 over 0 is actually infinity, right? That means this becomes infinitely, high. But when you have opposite charges, plus minus or minus plus, doesn't matter, then your U is negative, because one of the charges negative means the potential itself is negative. Then potential still 0, when R here is infinitely far apart, right? When the charges are infinitely far apart. But then as you get closer to one another, that means those two, as they get closer to one another, potential energy basically becomes more negative, right? So it gets closer, right? As R gets closer to 0, U becomes closer to negative infinity because of the type of, configuration you have. Okay. All right, so now what happens when you have multiple charges? For the multiple charges, then what you do here is you calculate, let's say, potential energy of the system. So for example, what you do here is, let's say you bring the Q prime here where there are already 3 source charges, right? Then what you do here is then electric potential energy is the algebraic sum. That means you have, U1, which is K Q1 Q prime over R1, then plus K Q2 Q prime over R2. That means this two interacting, and then those two interacting, and then those three and the other two interacting. So let's say, right, then plus K Q3 Q prime over R3 and things like that. So this is if you want specifically for this guy. So let's say take that to, from infinity and bring it to that point A. How much work do you have to do? So then you can, use this to calculate. Sometimes you might also have to be calculating, let's say, how much work needs to be done to set up some kind of, system of particles and things like that. We'll see an example. So let's say if you have a free empty space, you bring one, and then you bring the second one, you bring the third one, you bring the fourth one, you bring the fifth one, right? How much work do you have to do to, configure that? But right now, this is, let's say those 3 are sitting there. How much work you need to have, or you need to do in order to bring this Q prime over there? That means you have to make sure that it interacts with all of them in the, in the system. All right, so let's look at our first example here. All right, so we have 2 charges. Remember, when you're considering potential energy, electric potential energy is always between, charges, energy between two charges, let's say. Then one thing we can do here is this. So you have a point charge Q1, so that you can think like that's going to be, our source charge is plus 2.4 microcoulomb, is held stationary at the origin. A second point charge Q2 equals negative 4.3 microcoulomb, moves from point X equals 0. This is our point A, which X equals 0.15 meters, Y equals 0. That's the position of point A, which means right there. So it goes from this point A to then another point, which has coordinates of X equals 0.25 meters, Y equals 0.25 meters. So then this is the point B, and you're giving the coordinates. That means it goes from point A to point B. Then how much work is done by the electric force on Q2? All right, so let's see what we have. Well, let's say this is the displacement, right? So this is our delta S. That means it goes from there to here. If you try to use this equation, work done equals the force, then displacement, then cosine of theta, you're going to get a wrong answer. That's because the force at point A between those 2 particles is not the same as force at point B between those 2 particles. That means force is not constant. So do not use this equation here. There is an easier equation to use. Because one of the things we know here is this, right? Work done by electric force is equals to negative change in potential energy, which means this is energy at point A minus energy at point B, like we discussed. All I have to do is find the potential energy of the Q1, Q2 configuration at point A, find electric potential energy between those 2 configurations at point B, and just, find their difference between UA minus UB. And that's what we're going to do. So let's write down that RA is 0.250, sorry. So since this is the coordinate for RA, this is 0.150 meters. And then here RB, when they're, separated by this distance RB. Well, for RB, we're given that the coordinates here is 0.25, 0.25. That means, we're given these coordinates. So you can see, right, to find RB here, we have to then use the Pythagorean theorem, right? take the square root of, then 0.25 square plus 0.25 square to find RB. Okay, which we can calculate to be 0.3536 meters. Okay, now that we have sort of like those distances, right? So let's say RA and RB. What we can do here is I can then go and calculate UA. So UA is K Q1 Q2 divided by, Q1 Q2 divided by RA, which means 9 times 10 to the 9. Q1 is 2.4 times 10 to the negative 6 coulomb. Q2 is negative 4.3 times 10 to the negative 6 coulomb divided by 0.150 meters. All right. Now, remember again, not to put absolute value. What I get here is negative, let me put it here. So what we get here is UA equals negative 0.6184 joules. This is my UA. Same way I do UB. So UB here is equals to K Q1 Q2 over RB. So 9 times 10 to the 9, 2.4 times 10 to the negative 6, negative 4.3 times 10 to the negative 6, divided by 0.3536 meters. Again, negative should be there. So what we get for this guy here is the negative 0.2623 joules. Okay. All right, so let's see what we get. What do you guys think? Going from point A to point B, are we increasing our potential or are we decreasing our potential? So what do you guys think? Is this increasing potential or decrease? What I'm saying is UA bigger than UB? What do you guys think? So here's what I want you to guys understand. This is a scalar quantity, which means when you are looking at the number for the scalar quantity, negative is no longer a direction. There is no direction, it's a scalar quantity. So you're looking at them as just pure numbers. One is a negative 0.6184. The other one is negative 0.2623. So which, as a number, which one is greater? Well, you can see, right, this guy is greater. Why? Because it's less negative number than the other one. Just like, let's say, negative 4 is smaller than negative 2, sort of like that, right? Because this is a bigger negative, this is a smaller negative. And in mathematics, right, so negative 4 is, a smaller number than negative 2. Negative 2 is smaller number than negative 1, and so on and so forth. That means potential energy is greater at point B. Well, what does it mean? Well, it means that potential energy increases, right? That means we're increasing potential energy. Then what should you expect for the work done? Should you expect the work done to be positive or to be negative? Remember, this is independent of what we have. If the potential energy increases, work done should be negative. And that's what we're going to calculate. So work done, going from A to B, is UA minus UB. So if I calculate UA, negative 0.6184 joules minus UB, negative 0.2623 joules, then we're going to get this number to be negative 0.356 joules, which means the work done itself is negative. And if the work done is negative, then delta U here is always going to be positive, right? I'll put it like that. And that's what we had, right? I mean, if you do UB minus UA, you're going to get a positive number. Okay, that's kind of the idea. All right, so you can see, right, it's much easier to find work done using the potential energies between 2 points. And it, again, doesn't matter how we even get to that point. All we have to do here is find potential energy at point A, find potential energy at point B, and then do UA minus UB to find the work done. Here's another example. In this example, what we have here is this. The 3-point charges are on the x-axis. Q1 is at the origin, Q2 is at the x equals 0.3 meters, and Q3 here is at x equals plus 6 meters. Find the electrostatic potential energy of this system of charges for the following charge values, where Q1, Q2, and Q3 are positive 2 microcoulomb, when then Q1 and Q2 are negative, and Q3 here is, Q1 and Q2 are positive 2 microcoulomb, and Q3 is negative microcoulomb. Now, what do we do basically here? All right, so the easier way to think of it like this for this particular configuration is this. That means you are setting up this configuration, okay? So think like this, you start with nothing. So let's say here's the horizontal axis and you start with nothing. And there is nothing there. There's no source charges or anything like that. So then you bring and put the Q1 here with no effort. Okay, no effort because this particular Q1, right, has no forces pulling or pushing. You just put it there and that's it. No work needs to be done. But when you bring the Q2 here, well, Q2 here already has the Q1 there. That means there is to be work done because the Q1 generates now electric field, right? And then Q2 has to be then, you know, there has to be work done. There's a potential energy there. When you bring Q3, then there's again a potential energy, you know, there due to the fact that there's already Q1 and Q2 over there sitting. And that's what we're gonna do. That means taking this configuration, we can say that, you know, that it takes no effort to bring the Q1 there. But then when I, let's say, bring Q2 over here, I can look at that. There is a potential energy, you know, let's say stored when you bring Q2 where there's already Q1 over there. And assuming that we're bringing them from infinity, that means there is no potential energy there, right? So then this becomes K Q1, Q2 divided by R1, 2. Okay, so we have that. Now, when you bring then Q3 and you put it there, then Q3 has two fields, one from Q1, one from Q2. That means there's work done by each one, right? Then there's a potential energy due to each configuration. So then U2, which is, you know, going to be then Q3 interacting with them, becomes then K Q1 Q3 over R1 3. That means Q3 interacts with Q1, but also Q3 interacts with Q2. So Q2 Q3 over R2 3. Okay. So then what I have here is I have an interaction for all of them. That means I have Q1 Q2, Q1 Q3, and Q2 Q3. That means I'm looking at all those interactions and finding the potential. Then what I do here is I add them together to get the net. So the U net is equals to then K Q1 Q2 over R1 2 plus K Q2, let's say Q1 Q3, let's go in with order, over R1 3, then plus K Q2 Q3 over R2 3. And that's my total potential energy needed for that configuration. All right, so then from here what we have is that, so this is our equation, okay? And all you have to do here is calculate two different, you know, parts, right? For part A, part B. Part A, you just take then Q1 equals Q2 equals Q3 equals, let's say, 2 times 10 to the negative 6 coulomb. Okay. And then you take then R1 2 is equals to 3 meters, R1 3 is equals to 6 meters, and R2 3 is equals to 3 meters again. Okay, so those things won't change. But then what I do here is if I use things like this, so if I use all of those values with part A, that means I plug in Q1, Q2, Q3, right? All of those things in terms of 2 times 10 to the negative 6 and those distances, I'm going to get 30.0 millijoules. Again, all the work is done on my lecture notes, so you guys can kind of follow that. For part B, I have still R12 is equals to 3 meters, R13 is equals to 6 meters, R23 is equals to 3 meters, same thing. The only thing here is Q1 equals Q2 is equals to 2 microcoulomb, and Q3 is equals to negative 2 microcoulomb. Well, what it does, then you can see, right? See this term, everywhere there is a Q3, that term becomes negative. So this term actually going to be negative because the Q3 is negative. This term is going to be negative because Q3 is negative. Then if I plug in and then calculate that, that means I have one positive term minus something else, right? Because those are now become negative. What I'm going to get for this part B is a negative 5.99 millijoules. Okay, I trust you guys to that you can do just that plug and check type of thing. So then take just, plug those, Q's and, let's say R's, and you should be able to get those values. Okay, it just means that this is the total energy in my system with all of them positive. This is total energy in my system, like let's say potential energy, right? If Q3 is negative. Okay, you can see, right? Because one Q3 is negative, and I have two negative terms, and basically that negative term dominates. All right. Next, we're going to look at what we call a potential. So potential here is basically similar to the potential energy, but it kind of has a different, use. That means it's usually used for, let's say, more like, when you have circuits and things like that. And you can always find the potential energy using potential. And sometimes it's actually easier to use potential rather than potential energy. Now, generally, potential is a potential energy per unit charge. That means what one of the things we can say here is this. So we use capital V for that. So this V is not volume or velocity. And this V here is, using this equation, is potential energy. That means here's the potential energy, electric potential energy, divided by per unit test charge. That means here's one equation for the potential, for the potential. So this is sometimes known as potential energy, electric potential. So we call this just potential short. That means you have two things. V is the potential. U here is then potential energy. And make sure you guys understand the difference. That means if I'm asking you to give me potential, I want V. If I'm asking you to give me potential energy, I want U. If you ever have seen, let's say on a AA or AAA batteries, something like this, when it says V is equals to 1.5 volts, that actually gives you a potential, which generally what we have here is it gives you a potential difference between point A and B. So let's say here's point A and here's point B. So this is VA, this is VB, and let's say this is VA. Then the difference, if I write VAB sometimes, right? So sometimes I might put those things, sometimes I don't, so it depends. So generally I can let's say here's V, right? So VAB is equals to VA minus VB. This is a potential difference, okay? So sometimes known as voltage. So voltage itself means potential difference between 2 points. Now, one of the things we can do here is this. If I have then a potential difference, so let's say I have that voltage, right, VAB, 1.45 volts, using this equation, if I rearrange, you can see, right, then becomes U, electric potential energy is equals to potential times the test charge, like this, right? Test charge times the potential AB, like let's say. You can look at it in terms of this. Change in potential energy equals change in potential, like that. Which means that this is potential difference between points A and B. And let's say my Q naught is a proton, so E proton, just one proton. That means I can say that if this battery has a potential difference of 1.5 volts, that means potential at point A and B different by 1.5 volts, then potential energy for this proton is equals to then 1.6 times 10 to the negative 19 times 1.5 volts. And this will give me basically the potential energy, which is always easy if you have the potential. That means what I can do here is I can calculate potential energy between 2 points, not necessarily from the work done, but from the potential that I have. And this potential is due to the system itself. That means this delta V here is due to that, let's say the battery itself. And then when a proton goes from point B to A, right, I can calculate what will be the work done on it inside that battery. Okay. There is a little bit of analogy we can find in gravitational potential energy. Remember, gravitational potential energy, so here's the ground, and we could say that the potential energy, so let's say this is point A, this is point B, for example. So UB is 0. Why? Because remember, this is mgyb, and if I take yb to be 0, there is no potential energy there. Well, how about then UA? UA is going to be then mgh, so it's non-zero, right? Non-zero. Okay, but this is potential energy. But what we get here is potential is potential energy per unit test charge, which means that this potential is independent of the test charge itself. That means like it's some kind of scalar quantity that is true for any type of charge, right? Any type of test object, so let's say. Well, for the gravitational potential energy, we have this. See, if I'm considering this equation and I have two objects. So I have then object 1 and object 2. So U1, this is for point A, equals M1 GH. U2 is equals to then M2 GH. Are we going to get different potential energies, or are we going to get the same potential energy? What do you guys think? Think about it for like a few seconds. If I'm calculating potential energy for object 1 and potential energy for object 2 at the same height, are the potential energies will be the same or not? Well, remember, potential energy depends on the mass, M1, M2, and since M2 obviously going to be bigger, right? It's more massive, then U2 is going to be greater than U1. That means potential energy is the same only if the masses are the same. But if the mass 1 and mass 2 are different, at the same height, two objects have different potential energies. But think like this. So what if I'm considering this, some kind of quantity that is same for both of them? Remember, m is the mass of the particle, m2 is the mass of the particle, but see there's this quantity gh. See, they both have that gh. That means this quantity gh depends on the field that I have, g, and then the height that I have. That means this quantity gh is the same for all the particles, right? See, if I have this quantity gh, then what I can say here is this gh is there, well, even if I don't have any particles, right? If I don't have anything over there, right? If I didn't have those things, well, I can still calculate this gh is 9.8 meter per second squared. Let's say times, 10 meters. So this is 98, joules, and 98, let's say meter square. So let's say 98, just for a quantity, like let's say. Well, this 98 is there regardless of what I have, right? I have 1 kilogram object, 10 kilogram object, or no object at all. This 98 is there. Then one thing I can do here is then you can think of like this is then the gravitational potential, because this describes a point, right? So this point P, and how much height that point P, or some kind of quantity that that point P has with respect to Earth, which basically does all the work if necessary, right? And this GH then, GH is the same. And all I have to do here is, you can see, right? Calculate gravitational potential energy. Then I take its mass of a particle that I have, for example, mass 1, then times this quantity GH, which is, gravitational potential. Same thing, what we have is for electric. Then this becomes Q then times electric potential. That means this is kind of like equivalent to GH. That means electric potential between 2 points A, B is kind of equal to the GH, which means that it's the same for all of the particles. And then once you have different mass, you have different gravitational potential energy. Well, same thing is here. Once you have a different charge, then you have different potential energy. Which means if I go back here, so this 1.5 is there regardless what type of test particle I have. See, I said it's a proton. What if it's, a Q equals 5 nanocoulomb instead of just a simple proton? Then I will go here and I say, okay, so then it's 5 times 10 to the negative 9 times 1.5. Well, how about there's another one which is 15? Well, it's 15 times 10 to the negative 5. Then the U will change depending on the test charge, magnitude, right? But 1.5 is the same for all of them because 1.5 is due to the system itself, right? It's due to the battery rather than what type of charge is going through it. Same thing is here. So if you have two plates that we considered before, right? So you have two plates over there, then one of the things I can do here is this. I can have one plate to be positively charged, another plate to be negatively charged, just like the battery has positive terminal and negative terminals, right? So then what I have here is then VB, I can maybe set it to 10 volts, and VA, I can set it to 0. Then delta U, right, delta V, which is VAB, right, or VBA, doesn't matter, right, is then going to be 10 volts. That means just a difference between those two. Then what I have here is, that means the potential difference between those two plates is 10 volts for all of the particles that are going to be going from A to B, from one plate to another. Then how much potential energy, electric potential energy will they have? Well, it's then going to be their magnitude, then times this delta V, for example. So that's why if you have magnitude is Q, so then this is going to be, let's say, Q times 10. If your magnitude is 2Q, then it's going to be 2Q times 10. Which one has more electric potential energy? Well, obviously this guy, because it has more magnitude for the charge. While if something is 3Q, well, this will have more potential energy. How about potential? Well, the potential doesn't depend on the test particles. It just depends on the, those plates and how much potential those plates have. All right, so one more thing I want to talk about, for example, then how do we, let's say, make this guy here is 10 volts and the other one is 0? Well, we use, for example, a power supply or some kind of power source. See, for example, if I have one of those AA, AAA batteries, right? See, if I take the AA battery, so then what I have here is point A, point B, right? For example, then I can then take, remember this is 1.5 volts for the battery, which means that one end is higher than the other one by 1.5. For example, well, let me change this like this. So this is B, this is A. For example, if I then take B, I can say then VB is 1.5, then VA is 0. I take a cable and connect it to the one plate. That means this plate now going to have the same potential as the terminal B in the battery. If I connect this one to here, now this is going to be 0, which is the same as the negative terminal. That means then delta V, which is the difference between those two plates, is then 1.5 volts. You can see, right, it has nothing to do with the test particles I have. It's just basically, I'm connecting to some kind of power source, and they take the same potential as the power source itself. All right, so one equation, again, we looked at for the, similarities between potential and potential energy is this, right? So that means V, electric potential or just potential, is potential energy per unit test charge, okay? That means the electric potential V at any point in an electric field is the electric potential energy U per unit charge associated with the test charge Q prime at that point, okay? And potential energy and charge are both scalars, so potential is also a scalar quantity, okay? Now, the units are joules per coulomb, right? See, so V, sorry. So V here is equals to U per Q, right? That means joules per coulomb, but we define joules per coulomb to be as volt, or just V. So V is for volt, which is joules per coulomb. Okay, that means one of the things I can have here is I can find basically potential if I know the potential energy already, and I can find, let's say, then the potential different way, which we're going to see in a little bit, right? And one of the things we have here is, you can see, right, this potential is U per Q prime. In a way means that V does not depend on the Q prime at all. So then what does it depend on? Well, remember, Q prime is the test particle, and V depends on only the source particle. That means the source charge. So we're going to see that. All right, so like electric field, potential is independent of the test charge that we use to define it. Now, we can also have the collection of point charges. So for example, think like this. If I have here a source charge, Q, not Q prime, but a source charge. So then what we have here is all of the points around this source charge then have what we call this potential. Let's say here's point 1, so this is V1. Here's point 2, then V2, point 3, V3, and so on and so forth. That means what I have here is, I'm talking about, like, let's say distance R1 from this, distance R2, and things like that. That means what I can say here is this V1, V2, V3 is just a different distance from that source charge. And source charge is, only thing that represented in a calculation of a potential if you don't have, for example, any type of test charge. So this equation represents what happens if you have collection of charges. That means, for example, if I have this test Q, let's put Q1. This is a source charge. And here's point P. Well, this Q1 has a potential at that point P. Potential means that's sort of like a scalar effect at that point P. Let's call this V1 due to this Q1. Well, there could be another source charge, Q2. Well, Q2 also affects that point P. Well, it has then its own, effect, so let's call it V2. Well, then you can have another one, let's say, maybe negative source charge, Q3, then also has effect on that. That means the potential is kind of similar to electric field. Electric field is the vector effect of the source charges at that point P. Potential is the scalar effect of those source charges at that point P. All right, so let's look at then an example. Maybe it will help you kind of, visualize it a little bit. A point particle has a charge equal to +2 microcoulomb and is fixed at the origin. Okay. What is the electric potential V at the point 4 meters from an origin, assuming that V is equal to 0 at infinity? All right, so let's look at that first part first, part A. So you have some kind of a source charge. And this is, 2 microcoulomb. All right, so that means this guy has a scalar effect, right? So as I said, it's a scalar effect everywhere around it. And it depends on one of the things we're going to see, right? It depends on how far away it is from this point Q. So let's say here's the distances and things like that. So let's say then how can I find this V that is independent of the test charge? Well, remember the equation was potential energy per unit Q prime, right? Well, remember, what is U? U was K, Q prime over R. So let's say if I'm talking about this point P, which is a distance R from that point, from that, test charge, source charge. So let's say then this is divided by Q prime. And you can see, right, Q prime cancels out. That means V doesn't depend on the Q prime at all. What we end up here is this KQ divided by R. That means this is the equation for the potential at that point P. And it only depends on the source charge, KQ over R. That means I can always use this equation to calculate potential at some point around the source charge. I don't care if there is a test charge or not. This potential will always be the same because V is equal to 9 times 10 to the 9, which is the K, times 2 times 10 to the negative 6 coulomb divided by 4 meters, okay? And I can calculate then the potential, okay? All right, so let's see what we get. If I do that calculation, I'm going to get 4,494 volts. Or I can say V, where R is equals to 4 meters, is equals to then 4.5 kilovolts, right? Like 4.5 kilovolts. I can round it to, 1 decimal. Okay. So technically I should have 2 decimal. So let's, do our job. 4.49 kilovolts. So that's the potential at that point P. That means this is the scalar effect of that source charge. That means the potential is going to be 4.5, let's say, kilovolt, regardless of anything. That means this is an effect. It affects. That means any source charge has 2 effects on the space around it, and a vector effect, electric field, and a scalar effect, potential. Now, what I have here is then this. Remember, so this equation is another equation that we can use to find something like that, right? Potential around the source charge. Remember, so it says also that take V equals 0 at infinity. Why? Because see, if I say V when R is equals to infinity, is equals to KQ over infinity, and I get 0. That means its effect is 0, scalar effect at infinity, because if I go infinitely far away, the effect is going to decrease, decrease, decrease until it gets 0 at infinity. All right, so by the way, here's the thing. What if this charge was negative? What if this charge was negative 2 microcoulomb? Then I would have put a negative there, and then this would have been then negative. That means it's now a negative potential. You can have a negative potential because it's a scalar quantity. What it means here is that just like the potential energy, you do not put the absolute value, okay? So you do not put the absolute value. You need to use then positive, negative, if you have positive, negative, okay? So well, this was, let's get rid of that. So, okay, so this is what we have. All right, so let's look at part B. Part B says how much work must be done then to bring the second point particle, the test charge, right, that has a charge of 3 microcoulomb from infinity to a distance of 4 meters from the 2 microcoulomb charge. All right, that's also now, remember, work done, because the forces are, remember, force acting on those particles on one another changes with position. I have to use then the second method that I will learn, right? Which is going to be work done equals negative delta U. And what we have here is now, remember this equation, right? Delta U is equals to Q times delta V. I showed you that. Now remember, what we have here is this. We go from infinity to this position, right? We go from infinity to this position, okay? That means, we are going from infinity to this position. That means I can then take this equation where delta U is equals to Q times delta V, and I want to replace it, okay? But let me actually talk about this so then we can understand one thing very clear. Work done by the electric force will be negative delta U. But it says this is how much work must be done, not by the field, because field going to be doing negative work all this time. See, this is a positive source charge, and you want to bring another positive test charge to this point P from infinity. It wouldn't want to come because positive, positive repel. So we have to do work. We have to take it from there, and we actually have to push it all the way to this point P. And then when work is done by some kind of push or pull force, this is equal to delta U rather than negative delta U. Because when I'm doing work, not electric field, right? When I'm doing work, I transfer energy into the system. That means I increase the potential, okay? I increase the potential. Remember, you have work done by the field, but this is, I'm talking about the work done basically to bring that charge over there. Because, and what you can say here is that work done by this applied force, let's say, is equal to negative of the work done by the electric force. So that's why this negative, negative cancels out. Well, delta U here is equal to then Q times delta V. Well, remember, delta V here is the difference between infinity at point P, right? And their difference here is 4,500 volts, right? And my test charge is, a plus 2 microcoulomb. That means this is equals to, that means work done is equals to Q times delta V. So 2 times 10 to the negative 6 coulomb, that's the test charge, times the potential that I already have, which is 4,494 volts. Okay, that means I can, if I know the potential at some point P, and I'm bringing something from infinity, then I can use that to calculate the work done, which is then going to be equals to 13.5 millijoules. All right. So remember this equation, right? Work done by applied force equals to delta U, but then the work done by the field, electric field, right, is equals to negative delta U. So it's important to understand the difference. Okay, important to understand the difference, because work done by conservative force always equals to the negative of the potential energy, change in potential energy. Work done by non-conservative force, this is non-conservative force, is equals to always to delta U. Okay. All right, so a few things we have here is this. So we have what we call electric field lines, if you remember. And we said if you have a potential, if you have a positive test charge or positive source charge, sorry. So this is a source charge. So if you have a positive source charge, it has electric field radially moving outward. Okay. So that means electric field is moving outward like this. Now, what I have here is this. And if I look at the, this is the direction of the electric field, right? Radially out. So let's say, well, if I look at 2 points, point A, point B, and then if I look at VA potential at point E, VB potential at point B, one of the things I can see here is this. VA is going to be greater than VB. What does it mean? Well, VA is closer to the charge, means potential is greater than VB, which is a point B, which is further from the charge. So the potential at point A is greater than potential at point B. That means as I go in the direction of the electric field, right? If I'm going from A to B, V decreases as you move outward, which is the direction of electric field. That means if I go from A to B and A to B is in the same direction as electric field, I'm decreasing my potential. But if I go, let's say from here, from that point A to this point B, what I can see here is my V will increase as I move inward. Means that, well, as it says, right, VA, VB in this case, because VB is closer to the charge, it has higher potential. So if my path is in the opposite direction of electric field, right, which is direction of the electric field is outward, but I'm going inward, I'm increasing my potential. And this is always going to be true. That means, let's say you have some electric field. If you go from A to B, what do you guys think? Will I increase or decrease my potential? Well, here's VA, here's VB. Well, if I'm going in the direction of the field, my potential will always decrease. See, if I'm going in the direction of the field, I'm decreasing my potential. And that's always going to be true, regardless of what type of charge you have even. All right, so here's again, if this is electric field, I go from this point A to this point B. That means if I'm going in the opposite direction of the electric field, VA, VB, well, in this case, my VB is greater. In this case, my VA is greater. That means going in the direction of the field, I'm decreasing my potential. Going in the opposite direction of the field, I'm always increasing my potential, all right? Because in a way you can think like this. If I'm going in the direction of the field, I'm moving away from the source charge. That means my distance is greater, so my potential is less. If I'm moving in the opposite direction of the electric field, that means I'm going closer to the source charge and my potential is increasing. Okay. Now, that means moving in the direction of electric field means moving in the direction of decreasing V and vice versa. To move a unit charge slowly against the electric force, we must apply an external force per unit charge equal and opposite to the electric force per unit charge. An electric force per unit charge is the electric field. So then one of the things we can do here, there's an equation that relates those two. That means if I have a field, electric field, and if I know the magnitude of the electric field, so let's say this is 10 newtons per coulomb. If I go from A to B, for example, right? If I go from A to B, then what I can, and then D here is the distance, I can then relate those things. I can say then electric field is equals to the potential at A minus potential at B divided by D. That means electric field is equals to, see, VA minus VB technically means negative delta V over D, okay? So for example, let's say then I can use this equation technically to solve for delta V, which is going to be equal to negative E times D. Put it like this. So negative E times D, which means this. For example, if the distance here is 1 meter, then what I get here, negative 10 Newton per Coulomb times 1 meters, delta V here is equal to negative 10 volts. Does it mean that, does it make sense then the delta V is negative if I go from A to B? Yes, it should make sense, right? Because as I go from A to B in the direction of the electric field, my potential should decrease. So let's say that means, for example, VA is 20, VB now decreases, let's say 10. So that's why when I do 10 minus 20, I'm going to get negative 10 because I'm decreasing my potential by exactly negative 10. That means out of this, we basically get two equations, right? So this equation, rearrange it, right? Delta V equals negative E times D, or this equation equals negative delta V over D, or, you know, if you take this and rearrange, this becomes VA minus VB over D. Okay. And you can see, right, the units, 1 Newton per Coulomb for the electric field that we've seen before is also equivalent to potential in volts divided by the distance in meters. So volts per meter, that's also now a unit for the electric field. All right, so potential difference VA minus VB equals the work done per unit charge by this external force to move a unit charge from B to A. That means this is that equation, remember? So I said the work done is equals to Q times delta V, okay? So the work done by the field, right? Negative Q times delta V, which means then becomes Q times VA minus VB after I put the negative inside. Then this VA minus VB is equal to then work done by the test charge. This is the test charge, remember? So that's what we have. So VA minus VB equals work done by the Q prime. So when particle with charge Q, remember the test particle, moves from a point where potential is VB to a point where it is VA, the change in the potential energy is VAB equals UA minus UB. So this is kind of what we have, right? Because UA minus UB is equals to Q times VA minus VB, then we can just say work done is just in terms of then Q times VA minus VB. Exactly what I have over there. Okay. That means now we can find the work done two ways, by UA minus UB, or we can find the work done by Q times, you know, VA minus VB. Depending what's given, what's easier to find. And I'm always prefer the second one rather than the first one, okay? So for me, that's easier because it's easier to find the potential rather than potential energy. All right, so if charge Q is equals in, you know, the magnitude of E for the electron charge, and the potential difference is 1 volt, the change in energy is defined as an electron volt. Now, this is important to understand. So let's say we're going from point A to point B. And let's say we take VA, let's say VA and VB, right? So let's say VA is, let's say VA is 0. VB here is 1 volt. That means you can see, right? You're going through a potential difference of 1 volt. From A to B, you go through the potential difference of 1 volt. And then you have an electron there, right? then the change in energy, that means delta U, is equals to Q times delta V. Well, the Q here is the electron, which means negative 1.6 times 10 to the negative 19, right? And then delta V here is VB minus VA, right? Which is 1 minus 0. Yeah, so it's 1 volt. Okay. Then what we do here is we define this as 1 electron volt. See, this becomes a Coulomb times 1 volt, right? So then what we do here is this. So what we get here is this 1.9 times 10 to the negative 19 joules. That means that's the, sorry, 1.6 times 10 to the negative 19 joules. This is the amount of potential energy that you have, or amount of potential energy that changes as you go from A to B. Okay, so this is by amount of potential energy that changes. All right, so we define this amount of energy, 1.6 times 10 to the negative 19 joules, this amount of energy to be equivalent to 1 electron volt, which is unit of energy. Even though it says electron volt, but it's a unit of energy. That means it's equivalent to joules. You just, when you're dealing with electrons and protons and things like that, generally energy is very, very small. So what we do here is just we use electron volt as a unit of energy to make it a little bit more readable. So let's say 10, 20, 100, 5,000 electron volts rather than 10 to the negative 20, 30, 40, something like that. So just electron volt is another way of representing unit of energy. Okay. So again, so that's kind of like what we have. 1 electron volt is 1.6. Let me kind of like clear all this so you guys can see clearly. So electron volt is 1.602 times 10 to the negative 19 joules. They are equivalent. So make sure that you know, remember that, right? Electron volt is units of energy. One important thing we have here is about, let's say, remember metals, conductors we consider. I talked about before that inside the conductors, electric field is 0. That means, for example, if I'm doing the graph of electric field as a function of R, all the way to the radius, there is no electric field. It's 0. Only then at the radius, the electric field drops as 1 over R squared. It's not the same in terms of potential. So potential, on the other hand, is all constant and non-zero inside the conductor. So you can see, right, maybe let's say 10 volts, for example, right? So it's constant all the way inside until to the radius, right? Then after that, so if I'm considering potential at any point outside of the sphere, then it drops as 1 over R. But by the way, like let's say anywhere inside is constant. So at the center, anywhere inside is the same potential. So I can use that including the surface. So this equation basically gives you for the surface. Now, this might look a little bit different. What is this, had to do with the potential? Well, this 1 over 4 pi epsilon naught is actually same as K. It's in the, chapter 17 lecture notes. K is 1 over 4 pi epsilon naught. This is another way of actually writing K. So remember, K here is 9 times 10 to the 9 newtons meter square over Coulomb square. And here another new constant, this epsilon naught, sometimes like given like this epsilon naught, is permittivity of free space. It is equals to 8.85 times 10 to the negative 12 Coulomb square over Newton meter square. That means kind of like a reciprocal of that. So you might see that this epsilon naught used a lot, especially a little bit later on. So this is a permittivity of free space. And 1 over 4 pi epsilon naught is basically equals to K. Okay. So anyways, this slide basically tells you that if you are looking at the conductor, anywhere inside the conductor, potential is constant all the way to the surface. That means I can use this equation, KQ over R, the radius R, to find the potential at the surface. Means it's the same everywhere inside, from basically 0 to the radius, right? So R between, you can say like this, like that. Obviously, not exactly at the, when R is 0 because it will blow up, but let's say from there, maybe I should put like this so you guys understand, right? From, from 0 to, greater than 0, but less than or equals to R. But there is no electric field anywhere inside. Okay. All right, so one of the things I have here is this. So we just learned that potential is equals to, if you remember, right, E times D. So that's kind of the equation for the potential and electric field. Remember, there was a negative depending on, in which direction, let's say, what type of charge and all that stuff we have, right? But when you're talking about, let's say, just the magnitude, right? So you can say V is equals to ED. That means you can, if you know the potential difference between those plates, I can calculate the magnitude of electric field, which is V over D. So let's say if I have, this is positive plate and this is a negative plate, and I have, let's say, V for the positive is 10 volts, V for the negative is 0. Okay. Now, this is then sort of like, let's say, delta V. Well, what is delta V then? So delta V here is basically 10 volts. Let's say the distance here is 2 meters. Then this is 10 volts over 2 meters. So 5 Newton per Coulomb. Or, volt per meter. Remember, same thing, equivalent, right? Volt per meter, that's units for, electric field. That means all those electric fields have this magnitude, 5 volts per meters. Okay, so you can kind of always use that. Why do we need electric field, for example? Well, remember, I can use electric field multiplied by the Q naught, to find the force. Why do I need this? Well, if I have the force, I can calculate acceleration. Well, that means acceleration is equal to E Q naught over mass. Why do I need acceleration? Well, maybe if this guy starts from 0, I want to know what is the speed at the bottom. So then I can use V final equals V initial plus AT, let's say, or V final square equals V initial square plus 2 times acceleration delta X, right? Or delta Y or something like that. I can use these equations to figure out some of the things. What else can we do? Well, we can also do something different, right? We can also use energy. Always remember, we can use energy approach to calculate things. For example, I can say that I know, let's say here's that Y over there. So what I can do here is I can say, you know what? This is my point A. So let's say here it goes from A to B. Because electric force is a conservative force, I can say that at point A, my energy here is Ka plus UA. That's my energy at point A. At point B, then it's Kb plus Ub. Like that. Since we're dealing with the conservative force, EA is equals to EB. Okay. Now let's say this. Let's say if I put the particle at point A and I let go. Well, if I'm putting there at point A and letting go, that means there is no kinetic energy at point A. It starts from rest. Then it goes and reaches point B, which is then going to be my reference point, which means then let's say there is no potential at point B. Remember, potential at point B here is 0. So one of the things I can do here is this. So let me kind of give myself a little more room because it's important for you guys to know this way of working. So let's say what I have here is this. Energy at A is Ka plus UA. Energy at point B here is Kb plus Ub. My favorite way of writing this equation is this. Ka plus Q naught times Va. Remember, because U is equals to Q times V. Then this is equals to Kb plus Q naught times Vb. For me, this is better. Why? Because I know my V at point B. I know my V at point A. I know that at point B, there is no potential, it's 0. So this guy goes to 0. I know that I start from rest, so then this is 0. All I get then is Q naught VA is equals to KB. Well, if I know what type of Q naught I have, I can calculate this left side, right? Let's say it's a proton. Then this becomes basically E plus, right? Let's say. Can I calculate this? Yeah. Potential is 10. The E plus is just 1.6 times 10 to the negative 19. And this is equals to 1/2 mass of the proton, speed at b square. And then solve for the speed. That's it. It's as simple as that. That means we can always use this energy approach to solve for the speed. Can I use this too, the first approach? Of course. But this is much easier, believe me. All right. So let's look at then an example, kind of that we have something like this. All right. A proton is released from rest at point A in a uniform electric field that has a magnitude of 8 × 10⁴ volts per meter. The proton undergoes a displacement of magnitude d equals 0.5 meter to point B in the direction of the electric field. Find the speed of the proton after completing the displacement. There you go. That's kind of exactly what we want, right? Now, what I have here is this. I'm given the magnitude of the electric field. That means I'm given that electric field is 8 × 10⁴ volts per meters. We're given distance as 0.5 meters. All right, so what do I do? In a way, I'm given displacement, right? I'm given, like, let's say this D here is the displacement, E is the electric field, and I can use that, right, to find, I can use, and I know, remember, technically, and I know that my charge E, or like, let's say, Q is equals to E plus equals 1.6 × 10⁻⁹ coulomb. I also know the mass of the proton is 1.67 × 10⁻27 kilograms. Those are the things I'm given already because I know it's a proton. So I have proton's mass, I have its charge, and then I have, let's say, the distance it's traveled, that means displacement, and electric field. So I can use, in a way, because it's a uniform, right? I can use the dynamics and kinematics, right? So I can say that force equals ma, and force here is Q times E, or E times E, right? And then A is equals to E times E over mass. And then V final here is then the square root of, or let's say V final square equals V initial square plus 2A delta X, or, 2A times D, you can say that, right? And just plug in and calculate. You can do this. But, I can also use energy approach because I'm going from point A to point B. So I can say that because energy is conserved, because it's a conservative force, Ka plus UA equals Kb plus UB. All right, so we start from rest. This guy is 0. Then what I have here is this. We're given then it goes from top plate to bottom. So let's say I can say V plus, V minus. Okay. So remember, technically, we always take this guy to be 0. Right, so that means, the negative plate always, technically has potential of 0. But I don't have the potential. Well, I don't have the potential, but I have a way of calculating this. Because remember, delta V is E times D. That means I can say 8 × 10⁴ volts per meters times 0.5 meters. Meters cancel out, and I get, I get the volts, right? So which is going to be then, let's say, remember there's negative there, right? So negative 4.0 × 10⁴ volts. Okay, so like roughly 40,000 volts. Okay. And if I'm using this, then that means the delta V, right? That means what I have here is, as I go from A to B, I decrease my potential by that much, which means technically then this guy here is 4 × 10⁴ volts, and this is 0. So that's why the delta here is negative. Means that this here, what I do here is then I rewrite this as, let me do it first before canceling. Ka plus E times Va equals Kb plus Q is E, right? E times Vb. Well, Vb here is negative. Vb here is 0, which is negative plate. Ka is 0 because starts from rest. Then what we get here is this. E times Va equals 1/2 mVb. squared. That means speed at point B squared. And then just solve for that, right? So VB is equals to 2 times EVA, this is potential, over mass, and then the square root. Okay. All I have to do is just then plug in all the values, right? So remember, so let's say what I have here is 2 times 1.6 times 10 to the negative 19, then 4 times 10 to the 4 volts divided by mass, which is 1.67 times 10 to the negative 27 kilograms. Right. If I do that, then I'm going to get VB, speed at point B, right, is equals to 2.8 times 10 to the 6 meter per second. There you go. Using energy conservation to find that. Okay. All right, so a few other things here we have about, let's say, the electric potential. So just like you can see, right, this topographic map are curves of constant elevation and hence constant gravitational potential energies. We can use this to set up what we call equipotential surfaces. So for example, if you have a charge, it then has electric fields radially outward, right? So then, for example, if I choose some distance, so let's say think like this, here's the, the charge Q. See, let's say I'm choosing this distance R, and I'm like, let's say it's 2 meters. What is the potential there? Well, it's KQ over 2 meters. How about if I choose 2 meters here? Will I get a different potential? Of course not, because it's also KQ over 2 meters. How about here, 2 meters? Well, still the same, KQ over 2 meters. That means I can draw a surface like this, where as long as that surface is 2 meters, right, from the charge, potential is the same. So equipotential surface. Oops. So equipotential surface. That means if I choose something which is 1 meter, also same potential. 3 meters, same potential, and so on and so forth. That means what I can do here, I can have the surfaces over there around the charge where the potential here is the same. Now, what's the use for that? Well, one of the uses for that is this. At any point when I look at those blue lines, which are equipotential surfaces and electric field, they're always going to be perpendicular to one another. That means electric field is not something that we can see or even measure. Well, equipotentials are something we can measure. We can use an instrument called a voltmeter to measure the potential around a charge, or let's say some kind of conductor, right? I can find those equipotential surfaces. And then I can use that to draw the electric field because, let's say, for example, here's a charge. If I find this equipotential and then this equipotential and then this equipotential, then I can draw electric field because it has to be perpendicular, perpendicular, perpendicular. Here it has to go like this. It has to go like that. It has to go like this. That means they always have to be perpendicular to equipotential lines. That's something we're actually going to be doing experiment. So we're going to do an experiment and find those lines. All right, so field lines and equipotentials are always mutually perpendicular. And here you can see blue are equipotential lines, red are the electric fields. And you can always use that to get for any type of configuration. So this is something we're going to be doing in the lab. So I'm going to try to find a lab where we can do this. So we have positive, negative, right? Those dipole. And you can see, right, those are the equipotentials around this guy, equipotential around that guy. And we can then use them to map the electric field. See, perpendicular, perpendicular, perpendicular. It has to go perpendicular to this guy as well. And then perpendicular, perpendicular until it gets to the negative, okay? So we can see, right, we can actually measure the potentials easily using the voltmeter and draw those surfaces and use them to map the electric field lines. And then we can then go get all of those. Blues are equipotentials and red are the electric field lines. That means we cannot really see electric field lines, but we can draw them using the measured potential surfaces, okay? So you can even have something like this. You have a charge and then some kind of, plate. You can then draw, measure the equipotentials, draw them, and then use them to calculate then electric, or, not calculate, but let's say draw the electric field lines.